The different terms in the energy equation describe different modes of heat transfer. The second term on the left-hand side of the equation from the previous slide is the convective term. When a fluid moves, it carries heat with it, and this is what we call convection. Because the fluid carries the heat away, that means the solution to the energy equation is closely coupled to the solution for the velocity field. In Fluent, in order to compute convection, this means that you have to have the flow equations activated and turn the energy equation on. So whenever you're solving energy and fluid flow, then you're solving a convection problem. Some additional important points related to convection are: the rate of heat transfer depends strongly on the fluid velocity. So if you imagine a system like we see here on the right-hand side of the slide, where there's cool air flowing over a warmer body, the rate of heat transfer from the body to the air will increase as the velocity increases. Another point is that fluid properties can vary significantly with temperature, and you can define temperature-dependent properties in Fluent in the Materials panel. Generally speaking, the heat transfer rate is proportional to the temperature difference between the body and the free stream, and this constant of proportionality is called the heat transfer coefficient. For turbulent flows, the heat transfer coefficient at the wall is computed by turbulent thermal wall functions. The first term on the right-hand side of the energy equation that we saw a couple of slides ago is the conduction term. Conduction heat transfer is governed by Fourier's law, and this law says that the heat transfer rate is directly proportional to the gradient of the temperature. So in other words, the conductive heat flux is proportional to the temperature gradient through the thermal conductivity of the material. The thermal conductivity can be defined in the materials panel for both fluids and solids, and it can be a function of temperature or space or other things if you use a user-defined function. If a material is isotropic, then the thermal conductivity has a constant value, but for anisotropic materials such as composites, the thermal conductivity can be a matrix. Viscous dissipation converts kinetic energy to internal energy, so it looks like a source term in the energy equation. It's often called viscous heating because it's an irreversible process that increases the internal energy of the fluid as if it's being heated. Viscous dissipation is often negligible in incompressible flow. It becomes important when viscous shear in the fluid is large, like in lubrication problems, or in high-velocity compressible flows. As it was noted on an earlier slide, for the density-based solver, or for compressible flows with the pressure-based solver, viscous dissipation is accounted for by default. For incompressible flow in the pressure-based solver, the checkbox here in the Viscous Models panel controls whether or not viscous dissipation is included. If you want to estimate whether to include viscous dissipation in your calculation, you can use the Brinkman number, which is a dimensionless group that we see here. It defines when viscous heating is important, and this is the case when the Brinkman number approaches or exceeds unity.